Continue our conference, which we organized in the form of sequence of seminars. And today our speaker is Vassily Manturov from Moscow. He will tell us about free links. So welcome to Siberia, please.
Well, thank you very much. It's a great pleasure and honor of mine to give a talk at this conference. The aim of my talk is to tell about some combinatorial objects like graphs, which I will call free links, which turn out to be invariants of knotted objects. Actually, it was a very long story, and I will introduce some part of that story in the very beginning, how I was going to that. In fact, more than 10 years ago, I introduced so-called free links, which turned out to be discovered by Turaev maybe in 2004, and Turaev thought that they were trivial. And I not only found that they were not trivial, but I constructed invariants of three free links valued in more or less diagrams of links. So those invariants were not just polynomials or collections of groups, but they were containing link diagrams themselves. So they were saying a lot about geometry or combinatorics of objects themselves. And that was the initial point. I started thinking about, well, what can I do for classical knots? And it turned out that in the classical knot case, the approach I was considering was very much difficult. Well, more or less because classical knots do not have what I call parity, and more or less because, roughly speaking, because the plane where we project classical knot diagrams have no homology. Then I started thinking some other ways. Well, if we try
Since you have some problem with connection.
Yeah.
Yes, I see.
You mean internet connection? So can you hear me?
Now, yes.
Yes. Now, yes.
Okay. Excuse me. Yes. So
Just from now. Okay.
Just from now. Have you heard anything before? Have you heard what I said before?
Maybe just a couple of minutes of silence.
Oh, well, okay. So let me start with the introduction. This is more or less what I have said, that Turaev introduced the notion of free links. More or less, these are Gauss diagrams, modulo Reidemeister moves, when any crossing information is omitted. So when we consider just virtual knots and classical knots have Gauss diagrams with arrows corresponding to classical crossings, plus one more bit of information, which is the right number. So we have the arrow direction and the right number. We have 2 bits of information. What we can forbid, we can forget these bits and just leave them up to Reidemeister moves. So if we just forget over-under information, then we get what is called flat knots, flat virtual knots. So these are curves on 2 surfaces modulo homotopy and stabilization. And actually, those were classified, and more or less we can refer to some papers from the beginning of the 20th century, like those by Max Dehn. And actually, they have a very nice classification. So more or less, flat knots have a unique minimal representatives, except for some very special cases when we have some multiple knots or something like that. But we can go further and we can make one more simplification. So more or less we can have a graph of valency 4 for a regular graph. We can forget we can forget who is right and who is left. So having a crossing, we can just turn it over. And if we do that way, so we just record which edges are formally opposite. And this means that at the level of flat diagrams, we do what I call virtualization. So we flank a classical crossing with two virtual crossings. And unlike flat knots, free knots do not live anywhere, so they don't have any natural topology around it. And Ray first conjectured that they were trivial, and at that time I constructed invariants of flat knots, of free knots, just valued in diagrams of free knots, linear combinations of such diagrams, I would say. So my invariants were valued in linear combinations of frame for graphs. By framing, I mean the information of which edges are opposite. And linear combination, I was taking everything modulo Z2. So I was doing something at a very coarse level. I was considering some very rough objects, and I was constructing some invariants in Z2. And it turned out that for a very large class of links, we get such a very nice formula. I'm not going to get into the detail about free knots because I'm going to pass to their generalization, which I will call three free knots, three free links. And this formula meant the following. So I was doing some state sum by resolving certain crossings, but not all crossings. I was resolving only even crossings. And that way I stayed with what I had. I stayed with the collection of odd crossings. So for example, if my diagram was initially completely odd, then I could get such a formula because there was only one state, and then the state sum was giving me such a formula. And you see, in the left-hand side, I have I would say, a dynamical object, an object modulo some moves, an object I was studying as something to have an invariant of. And in the right-hand side, I had the same object, but just as a single graph. A single graph, well, strictly speaking, modulo Reidemeister 2, but graphs modulo Reidemeister 2 only are very simple objects. They have a unique minimal representative. So we can say that in the right-hand side, we have just one graph. So in the left-hand side, we have an invariant of knots. And in the right-hand side, we have just one graph. And this means that we can get such a nice corollary. So assume we have some k prime, which is equivalent to k. And actually, since they are equivalent, and since this bracket I constructed that time was invariant, this means that k prime contains k, because the way I was constructing this bracket was a sort of smoothings. So it means that I can formulate the following principle. If a diagram K is complicated enough, then whatever diagram I take contains this diagram inside itself. So, well, do I have pictures of cats? No, unfortunately. So actually there was a joke due to Lou about what can a categorification mean. So a categorification means a way of drawing a cat. So I did it many times in my talks. So I was considering a diagram as a sort of cat, and I was trying to do some Reidemeister moves, and whatever I do, I see this cat inside. So I was trying to construct not just a polynomial or just a group, but I was trying to consider invariants valued in diagrams of objects themselves. And actually, for virtual knots and for knotoids and for some other objects, it turned out to be quite effective. And so we can work not only over Z2, but also over Z. We can also add variables. We can add the information we forgot over under crossing and so on. But for classical crossings, it doesn't work directly. So then I started looking at, well, can we find some other homology, some other information like parity for classical knots? And then I thought, well, we can consider classical braids. If we have classical braids, then we can consider them as a dynamical system and of points in the in R2, and these points give rise to a configuration space, and this configuration space has a very non-trivial homology and homotopy, and we can study this homology and these homotopy groups. Homotopy groups are actually the braid groups, and we can study them by looking at this dynamical system. But how can we do that? Actually, if we look at the situation when points move on the plane, we can look at the following. I want to consider those situations when some 3 points are collinear. Actually, the collinearity of 3 points is a property of codimension 1. So if we have some property of codimension 1, this can give rise to some generators. So we can consider those are as some walls in the configuration space. What is the braid group? The braid group is the fundamental group of some configuration space. And how can we study some configuration space? We can construct walls. Walls and say, okay, walls correspond to generators. Walls are something of codimension 1. And if we want to consider some nice groups, we can look at the relators or relations which correspond to something of codimension 2. Say, if we have a point so that several walls are attached to that, we can go around that point, and this will be a small cycle homotopic to the trivial cycle, which gives me a sort of relation. So this led to another story which I was fond of for the last 5 years, and this story was called GNK groups, and actually we have already published a book with my collaborators, Denis Alexandrovich Fedoseev, Kim Sanjon, and Igor Nikonov, and actually Denis and Sanjon are my co-authors of this talk. And actually, the book was called Invariants and Pictures, and we were trying to compare invariants, which are valued in objects themselves, with pictures like cats, which always appear as subdiagrams of larger diagrams, and with words in, say, free groups. Actually, this has a lot to do with free groups, and actually, if we try to consider invariants of groups and homomorphic images of groups, we can consider everything as maps from some group to some free group, and this gives a lot when we consider braid groups. And actually, to complete this building, one thing was missing. In fact, I could do a lot for constructing some maps from the braid groups, and those are not virtual, those are classical. And actually, we can try to consider classical knots. So can we study classical knots by using these objects? So in fact, when we consider classical braids, we have what I call the GN3 approach. Why GN3? Actually, GN3, N is a subscript, 3 is a superscript, is the group which has choose N3 generators. I'm not going to talk about group theory today because I already gave a lot of talks, even in Novosibirsk many times. And I'm going to talk more about combinatorics and moves and so on. Actually, we have walls which correspond to something of codimension 1. We have walls which correspond to situations when 3 points are collinear. And this gives us another way of looking at braids. In fact, the usual picture when we look at Artin's presentation, Artin's presentation of the braid group, actually Hurwitz's presentation, it is just the situation when generators correspond to those situations when some 2 points turn out to be on the same vertical line. Indeed, if you have a dynamical system of points in R2, then we mark those moments when some 2 points have the same x coordinate by a generator. And this corresponds to how we get a word from a geometrical braid, and this takes into account only positions of couples of points. So in some sense, Artin's presentation is what we have for from GN2 theory. But can we do the same for GN3 theory? Well, the answer is yes, and all of these homomorphisms were constructed explicitly and calculated, and actually we have maps, and these maps are from the braid group to the group GN3, and it turns out that GN3 has a lot of very nice and easy surjective homomorphisms to products of free groups, and products of free groups look like very rigid objects. So if we have a word in some free group, in some standard presentation of the free group, then this word has a unique minimal representative. And this minimal representative is obtained by just canceling whenever we can cancel. Free group has no relations, unless those, except those which are going without saying. So free group has no relations, and its minimal representative is unique. And this is quite similar to the story of bracket of k is equal to k. So in some sense, those minimal diagrams of knots are similar to minimal words which have no cancellations. At the level of knots, minimality means no way to apply a Reidemeister 2 decreasing move. So a Reidemeister 2 decreasing move is the situation when we cancel 2 crossings, and at the level of braid groups, this means that we just cancel 2 generators. Now to complete the building, we can say, okay, we want to tackle classical knots. We have already got something for classical braids, but can we get invariants of classical knots? Of course, you can say, oh, okay, we have some objects when we have when we have 3 points on the same line, and this can be encoded by a graph. This can be encoded by a graph, and if we have such graphs, then this looks like something similar to a braid diagram, but these braid diagrams have triple crossings. And let's consider such braids, and maybe we can close them up to get a knot or a link counterpart. And this is what I will call 3 free knots and 3 free links. Okay, you can say, well, and let's go further, and possibly if we get a map from classical braids to say GN3 braids, then possibly if we close them up to get links, then we will get a map to 3 free links, which will appear just now. Unfortunately, the answer is not that simple, because sometimes when we apply easy isotopy to knots, which deal not only with braid-like moves, but also with minima and maxima, then it can happen that some minima and maxima can give rise to not just to some knot-like moves, but something like saddle moves. And saddle moves are something like cobordisms when we have, well, there will be a picture maybe somewhat later, but cobordism means that we have two strands with four ends, and we cut these four ends and reconnect them some way. And so if we do not have any way to keep track of how we reconnect during the cobordisms, frankly speaking, if we are given a graph, we can undo everything. Say we can cut away all vertices and reconnect whatever way, and there will be no chance to get a meaningful graph-valued invariance. And our goal is to construct graph-valued invariance of classical objects. And in fact, what is done in this work is we constructed an invariant of links up to link homotopy. So we know how to deal with invariants which were first considered by Miller and then by Levin, Habeger-Lein, and so on. But their invariants were just as collections of some new bar invariants. Well, anyway, there were some numbers of, or groups or something like that. And we have invariants which are valued in graphs. Well, in fact, there is some factorization, but small factorization. And actually, those will be valued in objects I'm going to call free links. So this was the motivation and what I'm going to talk about. Just one problem aside. So I started with virtual knots, and then I constructed invariants of classical braids. Now I want to pass to classical links, but there is a question, so what can we do for virtual braids? And then there is a nice question I'm very much interested in. The question is how to represent virtual braids by a dynamical systems. Well, in fact, when we pass from classical knots to virtual knots, we have to add handles. We have to add handles and pass from the plane to some handle to some thickened surfaces. We can consider braids on thickened surfaces, but braids on thickened surfaces are not the same as virtual braids. It's quite another object. We're going in some other direction. So the question is, can we represent virtual braids by dynamical system? And it's a problem. Now I'm past to the initial definition. My three links will be objects with triple crossings, actually regular four graphs, modulo some moves, and those moves will be a sort of Reidemeister moves, but I would say quadruple Reidemeister moves. So regular six graphs, which will have vertices of valency 6, plus some information about the ordering of edges. And then I want to make some equivalence relation, which is up to I can put some orientation on this frame 6 graph. And now let's welcome three free links, which are just regular 6 graphs modulo the following 3 moves. Actually, here you can see some analogs of Reidemeister 1, Reidemeister 2, and Reidemeister 3. So Reidemeister 1 is something when we can undo something very similar to trivial. Reidemeister 2 is when we undo 2 crossings, which are near each other, but in some sense of opposite signs. And Reidemeister 3, well, here I would say it's the tetrahedral move. This goes like this, and actually we can consider it as follows. So we can look at these at our objects as follows. So we have some points on the plane. They move, and whenever some 3 points, 1, 2, and 3, are on the same line, we want to put a triple crossing. But now you can ask, a triple crossing between what? So there is one natural way of thinking that in fact we have points and we trace their paths. So we have points and each point gives rise to a strand. So then a triple crossing will be like that. But the answer is no. I use another approach. Another approach. In fact, I want to consider not just paths of all possible points, but rather I want to consider the paths of pairs of points. So whenever I have n points, then I have choose n 2 pairs. And if I have choose n 2 pairs, then I can say, okay, if 1 and 2 and 3 are collinear, let me unite 1, 2, 1, 3, and 2, 3. And here, when I unite them, I will, so the definition as a text will appear some slides later. So when I unite them, I will have these 3 points on the same, these 3 points and at the same point. So I want to consider the modular space of pairs, and I have some walls which correspond to those triples of collinear points. In fact, of course, this relation is the most interesting. The third picture is what corresponds to the Reidemeister move or to the tetrahedron relation or the homologic relation. Maybe somewhere later we will have a relation. Yeah, here is the algebraic version of that relation. So there will be some groups, GN3 group, and some quotients of this group. And actually, this relation looks like that. IJK, IJL, IKL, JKL equals to the same in the opposite direction. So what does it mean? This means the following. Our paradigm is to consider something corresponding to codimension 1 to be generators. And something of codimension 1 or of codimension 2 will give rise to relations. So what sort of codimension 2 can we have here? Well, in fact, we are very much interested in collinearity. So 3 points can be collinear. Well, in fact, when we look at the usual Reidemeister in quotes theory, so we are interested in Reidemeister moves. What do Reidemeister moves come from? So we have 2 points with the same x coordinate, and if we have 3 points with the same x coordinate, this gives rise to the third Reidemeister move. So here we have a similar situation. 3 points which are collinear give rise to a crossing, and if some 4 points are collinear, then we have a quadruple crossing, but the quadruple crossing is not a stable thing. A quadruple crossing is something of codimension 2, and if we perturb it a little, this will give rise to 4 triples of points. So we can have 1 to 3 and 1 to 4 and 1, 3, 4 and 2, 3, 4. So we will get 4 triples of points. So 1 quadruple point will give rise to 4 triple points. So we will have 4 triple crossings. And if we perturb it in the opposite direction, we will get the same 4 points in the opposite direction. So this is more or less some higher analog of the third Reidemeister move. So this is what we have as an analog of the second Reidemeister move. And this is an analog of what we are going to have as the first Reidemeister move, but here we have a caveat. So actually, not everything is that simple. So if we want to close up, we can find a way to avoid Vortices and saddle moves. So actually, here are three free links, which are equivalence classes of such objects. So please, now I have three free links, and everyone is welcome to construct invariants of such objects. So I'm pretty sure many people can find lots of various invariants, so more or less what I have in my pocket is that three free links can be mapped to just usual free links. And if we have such a map, we know that free links have invariants valued in themselves, more or less. So we can consider the composite map. So we will get invariants valued in graphs. Well, of course, it would be better if we had invariants valued in regular 6 graphs, but so far it's not yet the case. But at least we have invariants valued in frame 4 graphs, and we have graph valued invariants, and we can make regular 6 graphs and 3 free links are invariant, are interesting by themselves. And the goal of today's talk will be a construction of maps from link-homotopy, from links to just 3 free moves. Unfortunately, this can be so far done only at the level of link-homotopy, not at the level of isotopy of things. Link-homotopy. So let me go further. So here I can consider braids. And for braids, everything is more or less perfect. So for braids, we can just consider pictures. And in fact, what I'm going to talk about now is just what I did before, maybe 5 years ago, just at the level of trivalent graphs. So I did it at the level of groups. So we have a dynamical system of points on the plane. And we have this dynamical system, and we have triple crossings. And we can just write down a sequence of generators. And what I had that time was, well, if we have a braid, we can write down a word, and this word will change according to some relations if we apply braid group relations. So actually, we will get a homomorphism from the pure braid group to the group GN3. And for braids, so there is no problem. And there is no problem for closed braids because they have no maxima and minima. For closed braids, we have something like 3 free links, but here we should not deal with the first Reidemeister move. We can consider, well, just objects by these 2 moves, the second and the third. So we will have invariants valued in these objects. So there is no problem to study braid isotopy classes valued in these objects. So we have this map. This map from braids to 3 free links with ends. So if we have a braid from one position to another position, or if we want to consider closed braids, we can just get a map to 3 free links. So these maps will be well defined because we just arranged moves to correspond to some codimension 2 situations. But the most attractive thing is what can we do if we deal with links or knots, not braids? You may also ask me, are there any other applications of this method? Well, any other objects? Well, in fact, one immediate thing one can get is that we can work not over R2, but over RP2. We can get planes and projective lines, and we get similar things. And actually, in fact, you can get not only 3 free links, but also 4 free links, 5 free links, and so on, corresponding to some properties which come from not triples but quadruples of points. And these quadruples of points appear for some other properties. Say for three points on the plane, we can consider the property of these 3 points to be collinear. And this is something of codimension 1. And if we have 4 points on the plane, we can say, okay, these 4 points belong to the same circle or line. So we can consider a straight line as an infinite circle. So in fact, there is a huge theory of G and K groups, and it's described in our book in more detail, but actually we have lots of instances when these 3 free links or maybe 3 free links with ends appear, but now we are going to deal with knots. So for braids and for conjugacy classes with braids, so I have already said it verbally, and now we can say we can look at the slides. So we did it with Nikonov at the level of groups, and so we can consider a diagram of our braid to be inside thickened torus or inside some annulus. So then we can then I want when I draw a braid inside an annulus, this is a part of notation. I can just take some point in the middle of my annulus. So my annulus is between 2 circles. I put my point in the center of the circle, and then I start rotating my ray, and then I have an angular coordinate. So it would be more convenient for me, and this is a part of notation, to consider closed braids with this angular coordinate phi, which is from 0 to 2p, and this coordinate gives me a possibility to close up my braids. So instead of just looking at some vertical coordinate, I want to consider some angular coordinate. And actually, then I just do what I did before. So I have points, and I consider the modular space of pairs of points, and I'm interested in those walls which correspond to triples of points which are collinear. And if triples of points are collinear, then we have 2 pairs of points, 1, 2, 1, 3, and 2, 3, which are collinear. And then I get a one-dimensional manifold, and whenever I cross this manifold, at the level of groups, I write down the generator I, j, k, where I, j, and k are numbers of these points. And at the level of graphs, I just put a triple vertex, but note that this triple vertex corresponds to I would say 3 strands, and these 3 strands are called ij, ik, and jk. So actually, the number of strands is so there are 2 versions: choose n2 or twice choose n2. I mean, so it can be n times n minus 1 over 2 or n times n minus 1. So, well, and then when I have A, B, A, C, and B, C, then I just create a triple crossing between 3 strands. And in fact, here, if I dealt only with braids or maybe with closed braids, and if I had no orientations, then you could just omit what is written in the second part of in the second half of this page. But if I want to deal with knots, when some points have orientations and my knot is closed, I can just put some orientation on those on that modular space. But this is quite easy. So, for example, you can just look at what we have at the level of braids when we have Reidemeister moves. So when we pass from braids to knots, well, strands can be oriented in the opposite direction. So this is something similar. So there is nothing very much complicated here. And in fact, here I just make some accurate way of creating the orientation. So how to orient ij, ik, and jk. So which one should be the first, which one should be the second, which one should be the third? Well, in fact, ijk, if j turns out to be in the middle, then the strand which goes to be in the middle would be ik. So we have ik in the middle. But in order to orient this triple, we should look at the orientation of the plane. And well, so more or less here we have the pictures how to orient ij, ik, jk. So, okay. In order to complete the picture of getting a free link from a closed braid. Well, and now the first main theorem, which is, I would say, preliminary main theorem, is that this map is well defined, and this theorem is actually already proved. So already proved because we arranged our two moves to correspond to something of codimension 2. Namely, we dealt with this tetrahedral move when we have four triple points, and we also have this second Rademacher moves when we undo two triple points of different signs. Actually, here we have a sort of orientation for two crossings, and they are arranged in such a way that if we go back and forth, then the two signs are opposite here. So this is sort of second Rademacher move. Actually, at the level of braid groups, we also have a relation which is called the far commutativity relation. But when we pass from words to graphs, this relation disappears. Namely, if we have points which move and give rise to a dynamical system on a plane, then we can have a relation which expresses the following. Here it is written algebraically somewhere in the end, and the relation is that if generators do not have so much in common, then they commute. Namely, this means that if we have, for example, ijk on the same line, and for example, ipq on the same line, and these two triples of indices share only I, then these two lines are different. So we have ijk and ipq. So we have two independent events. ijk are collinear and ipq are collinear. We have two independent events and they commute because we can first go through ijk and then ipq, or we can first go through ipq and then through ijk. So we have this commutativity. But this happens if our indices correspond just to strands. And in our situation, our strands correspond to pairs of indices. And for example, if we have, say, I, J, and K on the same line, then our strands are called IJ, IK, and JK. And from that point of view, when you look at, say, choose N2 or twice choose N2 strands, when you look at IJK and IPQ, so these two triples, IJK and IPQ, do not share any pairs. Because you see, you have IJK which gives rise to some pairs, ij, ik, and jk. And IPQ gives rise to IP, IQ, and PQ. So here you have 3 strands, and here you have quite other 3 strands. So this is why I chose pairs of strands, pairs of indices to correspond to strands. And this is very convenient, because then I have no trouble at all when dealing with this far commutativity relation. Well, of course, the way when strands correspond to initial points, they are also worth exploring, but then you will have another effect that you can have, for example, 1, 2, 3, and 1, 4, 5. They have one in common. And if you want to create triple crossings, which correspond not to pairs of, say, ij, ak, and so on, but just to numbers of points themselves, not paired, then you will have a very unpleasant effect. So this unpleasant effect means that you have 1, 2, 3, and say 1, 4, 5. Then you will have 2 triple points going through each other. So if you want to make this move on graphs, this will be a very unpleasant move, and it will be not very easy to handle it. So here you get this for free. So you have this theorem, and so this theorem is sort of preliminary, because you have Rademacher 2 and Rademacher 3. Excuse me, is everything okay with my sound? So I'm talking for
yes, everything's okay.
quite a while. So questions maybe so far. I'm talking for quite a while, so maybe you have comments. No questions. Well, so far, then I will go on. So in fact, the next step I want to deal with is to close braids up to get knots. Well, actually not knots, but links. Well, because if I deal with knots, then I will have to worry a bit about enumeration. Well, but enumeration is not a great deal, but in fact, I want to deal with links up to link homotopy. And here, I have a very nice situation, because we have a description of link homotopy by Lin Xiaosong and Nathan Habiger. And actually, this means that we can consider n component links up to link homotopy by using closures of n-strand braids. So we consider n-strand braids. So here I want to stress of the situation that the number n is the same. So in order to construct any link in the category of link homotopy, if I have n components, I will need a braid on n strands. Of course, this is not the case when I consider something up to isotopy. For isotopy, well, for knots, say 1 component links, of course, there is no chance to get anything non-trivial from 1 strand braid. So, right? So for 2 components, so I will have to increase the number of strands. And when I increase the number of strands, I will have to apply a certain sort of Markov theorem. So there are many Markov theorems for braid closures and for plait closures and so on. But in any case, when I deal with some sort of closures and I change the number of strands, then I get additional minima and maxima. And if I get minima and maxima which change, so then I can go through some very unpleasant moves, and these unpleasant moves can give rise to saddle moves on free links, on three free links, and these saddle moves spoil the situation completely. So that's why it is not that easy to do everything for link isotopy. But for link homotopy, the number of strands can change, but not very much. Well, now in order to do that, I will have to pass to Habega and Lin moves, and they will appear soon. Now, before passing to those moves, I want to show the situation when we have two maxima. Well, in fact, let's do the following. Assume we have a knot. And not say in R3, or maybe not in R3, but in say some full torus. So then I can have some coordinate. In R3, this can be a real line coordinate, and in the thickened torus, this can be a circular coordinate, the angle, and actually in some situations it's much more convenient for us to deal with a coordinate which is valued in S1, and in fact one has to study interactions between that theory I'm now talking about and Morse-Novikov theory, because when we deal with just usual Morse theory, then we can have minima and maxima. But when we have something valued in S1, then we can do without minima and maxima at all when we have braids. And this is very good when we don't have minima and maxima at all. But now, what is bad with maxima? So assume we want to deal with pairs of points. Now let's consider the situation when we have one maximum here, 1, 2. So we have the strand 1, which goes up, reaches its top, and then goes down, and here it is called as 2. And also 3, 4, another maximum. So I'm now interested in pairs of lines, in pairs of points. So here, for example, I have 1, 3. This is a pair of points which gives me a strand in some configuration space. When one goes to the top, by continuity, it changes to 2. And so 1, 3 gets connected to 2, 3. And by continuity, 1, 4 gets connected to 2, 4. But here, when we change the places of the two maxima, so when 1, 2 maximum is over the 2, 3, 4 maximum, then the situation changes drastically, because here we do not achieve the maximum 1, 2, but instead we achieve the maximum 3, 4. And the strand 1, 3 here gets connected to the strand 1, 4. And 2, 3 gets connected to the strand 3, 4. So our one-dimensional objects we get here, they just get cut and pasted. So we get a sort of saddle move, and so one-dimensional objects undergo very unpleasant transformations. And in fact, this is not a move allowed in the list of moves for 3 free links. This can be handled if we consider not just one-dimensional objects, but two-dimensional objects, but then we will have some sort of generalized 2 knots. In fact, if we can handle maxima, then we will succeed. So actually, we can ask the question, is it possible to consider knot theories when we do not when we do not have this situation with two maxima on the same line. Unfortunately, I don't know any link isotopy theory of that sort. Well, of course, we have braid theory. For braids, we do not have maxima at all. We do not have critical points. We just have some Morse-Novikov circle valued function, which is good. And when we pass to links, well, I would say at the level of link homotopy, we can do without that. And what about isotopy? Can you give me an instance of some knot theory when we do not have this move? If you do, then I will immediately have invariants which are valued in free links. But neither the usual Markov closure nor the Platt closure due to John Berman gives me such a possibility. But for link homotopy, this works well. So here we can just use the work by Lim and Habiger and take their moves from the pocket. In fact, so we do the following. We take our N-strand braid and we bow it. So we create such a bow and we will get a braid picture inside this horseshoe, I would say. So we have a sort of horseshoe, and then we can close it up, and we will get some sections of two strand braid. So we had N strands, and we create such a picture, we will get two N strands. So for example, here we have 3 strands, and here we get some section when we get 6 strands. So we have this operation. Well, unfortunately, there is no way, there is no obvious way back because sometimes it may happen that it's difficult to straighten up everything. But what is good here is that we have a 2 N strand braid group action on the N strand braids, because if we have such a horseshoe here, we can attach a 2 N strand braid downstairs. So if we attach such a 2 N strand braid, then we will have some object, and if we are lucky, we can consider it as another horseshoe. Habiger and Lin say that we can be lucky in this situation, and their theorem more or less says the following. So here are the 2 typical examples of 2 N-strand braids, which are in the kernel of what we get when we pass from braids to link homotopy. In fact, there are N-strand braids which are not isotopic, but which give rise to links which are link homotopic. Well, of course, there is the first theorem, which is the realization theorem, which says that all links up to link homotopy can be realized by N-strand braids when N is exactly the number of components. Here we can say that our braids are pure, and actually we can say that our braids are based. So we can have a collection of endpoints here. But of course, when we deal with link homotopy, we are allowed to do some crossings. So crossings mean the following. We allow any component to intersect itself. So we allow some component number I to go through itself. But it is not allowed for the component number I to go through the component number j if I is not equal to j. So, and here are 2 typical examples of what we can do, what we can end on the other side of the link. in order not to change the link homotopy type. So indeed, let's look at this picture. So here we, my strand number I goes around my, N goes around my strand number I. And here it goes around and creates the same crossing in the opposite direction. And in fact, if we close it up, then the crossings which appear here can be canceled with those crossings which appear here. But as for the picture, the two pictures we have downstairs, they do not just correspond to some crossing cancellation, but they also deal with the situation when some strand number I intersects with the strand number I. I will get in more detail in another slide, but actually it can be easily checked. It can be easily checked. Do you still hear me?
Excuse me, Vassily Legovich, we working already more than 1 hour, so how much time you need?
Well, I can easily finish it well in 10 minutes or 15 minutes. As
okay, so we don't need a break, so we can continue just in 10 minutes, okay?
Well, it's up to you. If you wish to have a break, I can make a break, so I can talk for
no, if you need only 10 minutes, we can continue, I suppose.
Yeah, okay. So well, now actually, what I wanted to say is that just these moves, which are given by Lin and Habiger, have a very nice interpretation at the level of three free links. So then we can say, okay, if we have 3 free links modulo something which corresponds to these moves, this will be this will encode very nicely something which corresponds to links up to link homotopy. And then the object we get, which will be 3 free links modulo some equivalence relation, will be again a very nice object which gets very nicely mapped to usual free links. And this quotient turns out to be trivial. So I will have some quotient modulo something, and this something will have a trivial effect when we pass from 3 free links to usual free links. And this will give me picture valued invariant, which is just the composition. So first we go to 3 free links. So here I have to impose something coming from Habiger and Lin. And this something turned out to be trivial at the level of usual free links. And then I will have picture valued link homotopy invariants. And then possibly, well, people know that maybe after the hop link, which is the simplest 2-component link, so let me now just go rapidly and say, so this is the theorem due to Habiger and Lin. So we have some way of taking quotient, and we know when they're link homotopic. Now we are realists and we have break closures. And here is the equivalence relation that we impose on 3 free links. And this is exactly the relation that we get. And this is exactly the relation that we get from Habiger and Lin. And in order to see that, I'm not going to dwell very much into the detail, but in order to see that, let me just show some, excuse me, no, excuse me, maybe this picture is not here, but let me just show yet another picture. So please believe me, that if I deal with this picture of Habiger link, this is just trivial when we close up the braid. And if we deal with this picture of Habiger and link, so we will have a sequence of moves of 3 free braids. And now attention, a sequence of moves when we do not have 2 maxima on the same level. And this is crucial for the whole construction, because here we can trace the whole configuration and everything is local and no saddle moves appear. And this is because our Morse function is valued in S1, not in R1. So then this will be the only relation we get from the Habiger link move. And this is link homotopy. We get a map from 3 free links modulo such a move. And then we can draw the example. This example is due to Kim Sun-John of the Borromean rings. And for Borromean rings, we can consider it as a closed braid, closed 3-strand braid, and it has complexity 6. You can say, okay, it has complexity 6 as a number of crossings of the usual braid, but I have another complexity 6 from another point of view, from the point of view of triple crossings. So I have 3 points on the plane, 1, 2, and 3. Then 1 and 2 can change their places, and when they do, then at some point, 2 turns out to be in the middle of the segment. So then I have 1, 2, and 3 on the same line, and then then 1 goes around in this direction. So I have 6 positions when 1, 2, and 3 appear to be on the same line, and I have 6 instances when I have triple points. So I want to create a graph. I want to create a 3 regular graph, so it has 6 triple points. It has 6 triple points, and these 6 triple points have to be connected, but this graph is highly non-planar because I have to connect them with some twisting, and so we have 6 true vertices, and all other crossings are just, can be thought of as just virtual. So this is what we get as a 3 free link, and so we get this picture for the Borromean ring, for the Borromean rings. And actually, it's not very much difficult to show that this 3 free link representative is minimal, so and minimal and unique, as the representative having 6 vertices. So any 3 free link diagram equivalent to that one has at least 6 vertices. So we say that the complexity of the Borromean rings is at least 6, but it's another complexity. It's not the number of classical crossings, it's the number of triple crossings. So we look at link homotopy from quite another point of view. Actually, this can be done when we map from 3 free links to usual free links, from when we, the way of getting from 3 free links to the usual free links is as follows. So actually, this is the theorem that we get a map from 3 free links to free links. I want to have a strand deletion map. So assume I have a 3 free link with n component, and I fix some component number I. I'm interested in those crossings when I participates. So for example, ijk, and I want to create a crossing jk from ijk. And if I had another crossing, say PQR, so that I is not among them, I just undo this crossing. I just do not look at that. So whenever I have ijk, I have this. So then I can get a map from 3 free links to 2 free links, and then it will be easy. And then it will be easy for me to get something for some well-defined map, and then it is calculated by Kim Sun-John that this gives me something non-trivial. So this is done at the level of groups. So we will have some maps to groups, and these groups can have some minimal representatives. So I go very quickly because I have to finish. So these are invariants. We can get integer valued invariants if we want, but we can do without. So this is the way how St. John proves that actually this graph is minimal. So at the level of free links, we cannot get less than 6 crossings. And so these are just some algebraic calculations due to Kim St. John. And in fact, for the Broman rings, we get a word of length at least 6, which says that we have at least 6 crossings. We cannot do less. And actually, they will appear in the same order. So this subword will appear in whatever word we want. And this is nice. And this is nice. And this is how we prove that the Broman ring is non-trivial. And we can do that for many Brownian links. But in fact, we haven't calculated much. And now I want to formulate some unsolved problems. Well, possibly the most striking problem is how to construct a variant of something modular isotopy using the above approach. So how to handle the problem with 2 maxima on the same level. So maybe you know some knot theory when we cannot go over this situation. I looked, for example, at Morse knots, but still we have some problems. In fact, this can be done if we do not restrict ourselves with one-dimensional formalism, but map from knots to 2 knots. But I want to have a one-dimensional formalism. I want to have a knotted objects like one-dimensional graphs with some crossings. Here I have to do something with maxima and minima. And so please, if you know any knot theory which can avoid these 2 maxima on the same level, I would be happy to deal with them. So another question is, well, we have link cobordism, but what about link? We have link homotopy, but what about link concordance? For concordance, it's not that easy because we don't have a nice braid presentation for that. So we still have to do something with knots, and since knots, then we have maxima and minima. So it's quite difficult. And then, of course, we can ask many questions about higher dimensional links and link homotopy. Well, we can ask because, well, we can tackle 2 knots or 2 links or higher dimensional links by making some dynamical systems and some movie moves. And it is well known that if we deal with just dynamical systems of points, so when we deal at the level of braids, then we can do it in any dimension. For example, dynamical systems of points in R3 or in R4 can be nicely described by groups G and K for some appropriately chosen K. But this is still the level of braids. We can do closed braids, and there is no problem, but I want to do links. And for links, it's a problem still because of maxima, so we can look at other G and K theories and try to handle the situation with maxima. So which knotted objects, cobordisms or concordance or high dimension links up to link homotopy can we handle by using this approach? So here I would like to start. So here is some list of references.
Okay, thank you very much. Thank you.
Thank you.
And so please, questions, remarks, comments?
Could you say a little more about the problem about the maxima and trying to get invariance of isotopy?
Yes, so the problem is as follows. So here we have a picture when we have 2 maxima on the same level. So I'm now considering the configuration space of pairs of points on the same level. And if I have the maxima 1, 2 here and a 3, 4, which is higher, then 1, 3 gets connected to 2, 3, because I go this way, I reach this maximum, and here 1, 3 gets connected to 2, 3, and 1, 4 gets connected to 2, 4. And if the other maximum is higher, 1, 2 is higher, then 1, 3 gets connected to 1, 4, and 2, 3 gets connected to 2, 4. So what happens with these lines, they undergo a saddle move. And objects, when saddle move is allowed, are very hard to deal with. So that's the problem with two maxima on the same level. So I consider the moduli space of pairs of points. And when I do some isotopy, it may happen that here I get saddle moves. And that's the problem.
Thank you.
Well, and yet another thing, if we consider not the configuration space of pairs, but the configuration space of points themselves, then the unpleasant thing which can happen is that triple points can go through each other. So we may have the situation when, say, 1, 2, 3 commutes with 1, 4, 5, and this means that some triple points on the line 1 goes through another triple points on the line 1, which is unpleasant. So we have one triple points going through another triple points, and it looks bad. So that's the problem. Well, and I want to repeat that next week on Tuesday, and then on Friday, and then the next Tuesday, I will be given a short course of lectures in the Yale Institute at Tsinghua University. I will tell in much more detail about the parity bracket and GNK theory and this approach to link homotopy valued in 3 free links.
Okay, are there more questions for today? Some comments, some remarks, please. If there are not, so let us thank speaker again. Thank you very much for interesting talk. And our next seminar will be next week, yes?
Yes,
June
on Wednesday,
9th,
as usual.
as usual. Yes. Okay, thank you very much for attention.
Thank you.
Thank you very much.
Thank you.